Hello everyone, I'm back for another video finally. I thought for a long time about what my next video should look like, and every time I tried to make one, I just felt like I was ripping off my own probability professor and just following his course to the letter. So I finally came up with the idea that I would kind of intersperse that inevitable copyright infringement with some like undergraduate probability material to kind of make a connection between the rigorous mathematical stuff and maybe some more intuitive subjects. So now that we have this idea of the probability space, I want to relate it to something, the more familiar form of probability that we're used to seeing, like things like probability of coin flips and dice rolls and things like that. So all of these things, I'm not going to talk about either of those actually in particular, but they all fall, both of those things fall under this category of finite sample spaces with equally likely events. So that is what I'm going to be talking about today. So just remember from the first video what our definition of the probability space is. We have a set omega of outcomes or sample points, if you prefer. We have a sigma algebra F of events, so collections, these sets of sample points, these measurable sets. Then we have a probability measure, and that's a positive set function, finite measure. So how does all this relate to what we're used to dealing with, which is probably in most cases just finite sample spaces? So let's say we have a set omega with just n elements. So this could be like the set of all dice rolls. Like if we roll a single die, this could be the set of all outcomes of the dice roll, which would be like 1 to 6, right? Or if we do coin flips, we could think of that as just, it's got 2 outcomes, 1 and 2, like, or heads and tails, which we could denote numerically. And then we could think of the sigma algebra on omega as the power set, just all subsets. Then if we would like all of these possible outcomes or primitive events, elementary events, if we would like all of those to be equally likely, what does our measure look like? What does our probability measure look like? Well, we know we want the probability of all of omega to be equal to 1. So we have 1 equals the probability of omega. And then since omega is just the finite disjoint union of all those sample points, and there's n sample points, we have that the probability of omega is equal to the union of the sample points. Since these are all disjoint, we could think of it as the sum of the individual sample points. And if they're all equally likely, then we could pick any index I. This could be probability of 1 or 2 or whatever. They're all the same, right? So let's just leave it as P of I. And then this collection is just n times the probability of one of those, right? So our probability is n times P of I. And so on one hand, we have 1 equals the probability of omega equals n times probability of one of those individual outcomes. So we naturally get 1 over n equals probability of I, where I is any one of those outcomes. So just this. Okay, so it kind of matches with our intuition, right? If I roll a die and all sides of the die are equally likely to come up, well, there's 6 sides of a die, so the probability of each side coming up is 1/6, right? So it's just a little formal way of matching our intuition with the idea of this probability measure. So in this scenario where we have a finite sample space and all these events are equally likely, then the probability measure really just becomes a matter of cardinality of a set. So the probability of some event A, okay, so P of A becomes the cardinality of A divided by the cardinality of omega. And so measuring the probability of events really comes down to counting the number of elements in our event A, or whatever set we're talking about. So really, when I think counting and things like permutations, combinations, really that's all combinatorics, right? So really, what we're going to be using mostly for these finite sample spaces is like techniques from combinatorics. So just a quick example. Let's say we have 2 cards randomly selected from a deck. What's the probability that those, when I take those 2 cards together, I have blackjack? Meaning, hopefully you guys know what blackjack is. So we could think of omega, our set of all possible outcomes. Like if I just choose 2 cards at random, what's my omega? It would be the all possible pairings of 2 cards, right? How many elements are in omega? Well, I choose a first card from, there's 52 possibilities, and then once I've chosen that first card, there's 51 cards remaining in the deck, right? And I choose one from there, and so there's 51 combinations. So there's 52 times 51 elements in big omega. And if they're each equally likely, then the probability of any one particular pairing is 1/52 times 51. Okay, so now let's think about what the probability of getting a hand of blackjack is if we only take 2 cards. So first, let's think of this really from the ground up. There's 2 ways to achieve this, right? Maybe I choose cards in order. Okay, so let's first think about it in this context. I choose one card, look at it, and then I choose another. So there's 2 ways to achieve blackjack, right? Maybe the first card I choose is an ace, and then the second card would have to have a value of 10, right? So it'd be a 10, jack, queen, king. Or maybe the first card I choose has value 10, so 10, jack, queen, king, and then the second card I choose is an ace. So those are my 2 ways to achieve blackjack. So let's focus on this first. Let's find the probability, or really we're talking about the cardinality, right? So how many elements are in this set? Let's say this set is we could say A is the set of combinations that give us blackjack with 2 cards, right? So we could say this. So to find the probability of A, I need the cardinality of A over cardinality of omega, right? We already said that the cardinality of omega was 52 times 51. So now to find this probability, I just need to find probability of A. Okay. These 2 things combined will give me my set A. So let's first figure out how many ways to achieve this outcome are there? How many elements in this event are there? All right. How many ways are there where I can choose ace as my first card and then a 10 valued card as my second card? Well, let's look at our aces, right? So let's assume our first card is an ace. And there's 4 types of aces. There's 4 suits: hearts, diamonds, spades, clubs. Okay. So let's start in this top left corner here. Let's say I pick an ace of hearts. Now, and let's just fix that ace of hearts. How many ways are there to get blackjack if the first card I have is an ace of hearts? well, my ace of hearts, I could pair that up with a 10 of hearts, or I've drawn all the connections with the aces and the tens. So maybe I might pair up my ace of hearts with a 10 of hearts, or a 10 of diamonds, or a 10 of spades, or a 10 of clubs, right? So if my first card is an ace of hearts, there's 4 possibilities for choosing a 10. And then there'll be 4 possibilities for choosing a jack, which I've drawn in blue here. And then 4 possibilities of drawing a queen or a king. So if my first card is an ace of hearts, I have 16 ways to get blackjack. And same thing if my first card is an ace of diamonds, I'm going to have 16 ways of getting blackjack if my first card is ace of diamonds. Same thing with ace of spades and ace of clubs. So in total, there's going to be 64 ways to achieve blackjack if my first card's an ace and my second card is a 10 card, right? And similarly, there's another 64 ways where I choose a 10 valued card first and then an ace. So in total, there's 128 ways to achieve blackjack with 2 cards. All right. And we know that each of those has a probability of 52 over 51, or 52 times 51. So what we've just said is that the cardinality of A equals 128. And we know from previously that the cardinality of omega is 52 times 51. So the probability of A is 128 over 52 times 51. Now, this is really the kind of most bare bones way to think about this and compute this probability. The tools from combinatorics are just going to make this easier. So maybe you have taken an undergrad probability course and you already know, hey, there's an easier way to do this. We could use things like the choose function, the binomial theorem. We could use the binomial theorem. And there's a lot of these tools like this from combinatorics, but they're all just achieving this same idea of basically computing the cardinality of these sets. So let's look at this nice tool we have from the binomial theorem to compute this same probability in a much more efficient manner. So I have this neat little formula that gives me my probability. So I know that how many ways are there to choose one ace? Well, there's 4 possible aces, and so there's 4 choose one ways to choose an ace from that set of 4 aces. And if I want to get the number of ways to choose one ace and one 10 valued card, that's going to be 4 choose 1 times 16 choose 1, where 16 choose 1 is the number of ways I can choose one value, choose one 10 valued card from the group of all my 10 valued cards. So all my 10s, jacks, queens, kings. There's 16 different ways to choose one of those cards, right? And then there's 52 choose 2 total 2 card combinations. So essentially what this numerator is giving me is the cardinality of A, and then what the bottom is giving me is the denominator is giving me is the cardinality of omega. Okay, so that's all these nice tools from combinatorics are giving us. They're just giving us these ways to compute these cardinalities, which really just gives us our probability measure. And we see the answer is equivalent. So really that's all I wanted to present in this video, a little connection between the idea of the probability space and the more intuitive idea we might have from undergraduate probability. A good book for this would be Sheldon Ross's First Course in Probability. Chapters 1 and 2 would be kind of where we're up to right now. After this video, you should be able to do those with a little maybe extra studying from that text. If you've never had any kind of undergraduate probability, you should be able to catch up on that fairly quickly. So that's all I had for this video.